Hello everyone. Today we're going to do some analysis on search algorithm. Assume that you have some numbers from let's say 1 to n. So let's say an sorted array, and you want to find some key, let's say x, in this array. And as we said, array is sorted. So you can use, for example, the binary search for finding the item. Here you see a decision tree for this binary search. So with 7 items in the array, or the item like the list that we have that are sorted. First, we are searching the number x at the middle of the array. That here in this case is S4, and S4 stands for the item number 4 in the sorted list or array that we have. If I forgot to put this one. So if the item that we're looking for exactly as the middle of the array or the list, then we are done. So it should return the value x as the index. And if the number that we're looking for is greater than the item at location S4, then we are searching the right side of the array or the list that we have. So the same approach until we are returning, showing that it should return 0. That means that the index hasn't been found, okay, or returns the proper index. And here we assume that the items start at index 1 and not index 0. So that's why we reporting index 0 as like showing that the item has not been found. So based on this, we can define what's going to be a valid decision tree. So a valid decision tree for searching operation, when you have n keys and we're looking for a key like x, then it means that we should have, for each possible outcome in this search, we will have a valid path that goes from the root to the leaf. So here, for example, as you see, for every the value of x that we are going to have, it's compared with all the the values that we have, and at the end it reports the proper value. So it's a valid decision tree. And also we call a decision tree a prune if every leaf is reachable from the root. Okay. Before when we were talking about the sorting algorithm, we showed that how a tree, for example, can be not pruned. Okay, but if every leaf is reachable from the root, then it is called a prune tree. Now, based on this definition of valid and pruned, we can say that every searching algorithm has a corresponding pruned valid decision tree. And it's not hard to see that, okay, but if you just look at the definition, okay, of the valid tree and also the pruned tree, you can easily see that it is true. Okay, before continuing our analysis, let's look at this lemma. So lemma 1 says that if n is the number of nodes in a binary tree and d is its depth, then we have d is greater than or equal to the floor the floor of the log of n. So we are going to see that how we can show this lemma. To prove that, we're looking at the definition and the features of the binary tree. So let's say that we have a binary tree that has n nodes. Okay, so at the first level, that is also the root, we have only one node. Then at the second level, we have 2 nodes at most. Okay, and the next one we have 2 to the power 2, because every node at most has 2, and until we reach the depth of the tree, that is 2 to the power d. So definitely the n will be less than or equal to this number. This is when we have a complete binary tree, and n is definitely less than or equal to this number. If the tree is complete, then n is equal to this number on the right side. Otherwise, n is less than this number. But we know that the summation of 1 plus 2 to the plus 2 to the 2 plus until we reach to the d is equal to sigma of I equal to 0 to d of 2 to the power I. And this is equal to 2 to the power d plus 1 minus 1. So we can conclude that n is less than equal to 2 to the power d plus 1 minus 1. That means that n is less than 2 to the power d plus 1. And also this means that if we just take the log from the both sides, then we will have the log of n is less than d plus 1. So we're going to get rid of the number 1, so it means that the floor of log n is less than equal to d. Okay, so that's how you can show this lemma 1. Now let's take another look at another lemma. Lemma 2 says that to be a prompt valid decision tree for searching n distinct keys that we're looking for key x, the binary tree consists of the comparison nodes must contain at least n nodes. Now we're going to show how we can prove this lemma. We're going to prove this lemma by using the contradiction. So assuming that there are fewer than n comparison nodes, okay, so there are two possible ways to have this situation. One is that for some I, let's say that for some I, a subscript I doesn't occur in any comparison node. Okay, so we don't have this comparison of Si with the key x. Or we have some I that Si is never compared with x, but it is compared with some other nodes, other items in the array. Okay, so not by x, but maybe by some other like Sj in the tree. So let's see the first case. Assume that we have two inputs, input 1 and input 2, that are all identical, okay, except then we in one of them we have the Si, a subscript I, and the other one we have the instead of Si we have Y, and Si and Y are not equal to each other. So using the decision tree, okay, both gonna give us the same result. It means that the x that is equal to Si has not been found. But as we know, a correct decision search algorithm should say that in the input 1, the value x is found at location I, so it should return I. So that contradicts with our a correct search algorithm that the result should be this one should return I, but both returning the decision tree, both returning nothing, or returning like for example the 0. It means that the index has not been found. The other case was that we said that for some I, Si is never compared with x, but it is compared with another item in the array. Again, we have let's assume that we have the two inputs. Okay, they both are identical except the item location I, that here we have the S at I and Y. But here, in this case, we're assuming that Si is the smallest key in both inputs. So, and also the x is one that we are gonna look for, and x is equal to the Si, and one of the input. Let's say here is input 1. So the decision tree then will generate the same result, says that the x is in any of them, okay, because we said that is not gonna, our assumption was that it doesn't compare with the x, but it's gonna compare with other nodes. Okay, also the second one, the x doesn't exist, okay, so it's returned like for example 0, or the invalid index says that the index has not been found. But the correct search tree will say that we'll found the x at location Si at location I, so it contradicts with our assumption. So with this we can prove this lemma. Finally, let's look at this theorem that says that any deterministic algorithm that searches for a key x in an array of n distinct keys only by comparison of keys must, in the worst case, do at least the floor of log n plus 1 comparison of keys. The proof is really easy. So we showed lemma 1 and lemma 2 that in lemma 1 we said that the depth of the tree is greater than or equal to the floor of the log n. Also, by lemma 2 we said that the binary tree must have at least n nodes. Okay, so the worst case number of comparison will be the floor of log n plus 1. And also, this comes from this fact that the worst case number of comparison, okay, is the number of nodes in the longest path. Okay, the longest path, that is gonna be the depth of the tree plus 1. The longest path is gonna be the number of comparison. It's gonna be from the root to the leaf. That's gonna be log n plus 1. So finally, the worst case number of comparison at least will be floor of log n plus 1. And this we can with this we can conclude that the binary search is optimal in the worst case.